Okay, so today's lesson is about graphing our polar equations, and we're just going to graph a few of them. I have pictures of them listed right here. Let's talk about each one. The first set are, let's highlight there. So it would be like r equals a number cosine theta or r equals a number sine theta. And what that generates is a circle. Okay, that generates a circle. There's certainly no reason that you need to memorize all of this. I just really want to give you kind of an idea of what we're going to be doing and what the equation would look like if you wanted to know which kind you were going to be graphing. So if it's simply a number times cosine or a number times sine, that's going to create a circle when we graph. If we have something that is like a number plus a number times cosine or sine, or minus, plus or minus a number, it's going to generate one of these four graphs. And so it could also be a sine, because either sine or cosine, we'll be doing both sine and cosine. And if you wanted to know, you certainly don't have to memorize this. There's no reason why you have to know this. But if you wanted to know what kind of these graphs you would generate, you would take this number, the number A and the number B, and if you divided them, and that number was less than 1, then you would have this inner loop going on. If you divided those two numbers, and we're not going to do that, I'm just trying to describe, if you wanted to know a little bit more information about what you're getting ready to graph, you certainly could do this. If you divided those two numbers and you got 1, it's going to create a cardioid, kind of looks like a heart. And then if the division of those numbers is between 1 and 2, you would have like almost a cardioid. It wouldn't quite come to a point. And then if those numbers divided were greater than 2 or equal to 2, you would have kind of like almost like an ellipse. It's just like this one side is a little bit flatter than the other side. So that's that kind that we'll be looking at. The next set have to do, they call them roses. I don't know, they kind of look like daisies to me, but maybe that's not as pretty of a name as roses. So that entails, let's look at this. So we would look at r equals a number times sine or cosine, and it'll be it'll be like a double angle or a triple angle or a quadruple angle. The n is going to be some number that's not 1. So if that number n is an even number, then the number of petals you're going to get on your rose would be twice that amount. So for this first case right here, this would be an n of 2. An n of 2 would create that 4 petals like you see right there. And the same over here, an n of 2 would create 4 petals. Notice the difference in the orientation. If it's sine, the petals are oriented like inside each quadrant. And if it's cosine, the petals are oriented like on the axes. Again, you don't have to memorize that. I just want to point out patterns that are possible for you to take a look at to see what's coming. So that's what happens if n is even. If n is odd, if n is an odd number, then the number of petals are going to be the same value as n. So if we were looking at this graph, this we would know would be an n of 3. That graph would be an n of 3, and that's a sine graph of an n of 3. And this one is a cosine graph of an n of 3. And that's the next, these right here are the next type that we would look at. There really are 4 types of graphs we're going to do today. The circles, the cardioid-like graphs, the roses, and this last one is, actually it's a little strange. This is a bit weird because it's an r squared. So with this one, let's just kind of focus on this scenario. It's r squared. That really changes things for us. When that's r squared, what happens is this 2 which is like an N of 2, would normally mean that we would have 4 petals. But when it's R squared equals, what happens is the negative petals are eliminated, because we know that if R squared equals a number, it can't be negative, right? And if we were to square root both sides, we know, so if we were thinking through, we know that the square root of 4 cosine 2 theta can't be negative. So instead of having 4 petals, like, it would be if it was just 4 cosine 2 theta, it's going to have 2 because 2 are eliminated. And we're going to graph one of each kinds of these to give you a better idea of what that would look like. Okay, so that's kind of our goal for today, is we're going to look at graphing each of those, and I'm going to show you what I think is the easiest way to do this. There's a couple of different ways you can do it, but I like the way I'm going to show you. So are there any questions so far about just there are 4 different kinds of polar graphs that we're going to be working with? Okay. So let's look then at our first examples. Okay, so the way that I would recommend, what we need are points to plot. We need points to plot. And I think the easiest and most effective way to do this is to draw the Cartesian coordinate graph of whatever we have. This is 4 sine. So this is going to dig back into your memory banks. We have done this already, and these are going to be fairly straightforward and easy graphs. The graphs are all either sine or cosine. And so easy as compared to what we were doing when we were graphing. Remember, there were like 4 or even 5 different transformations we could do. This is going to be very limited. So this amplitude, that is the amplitude, is 4, and our B is 1. So we know that we've got just a regular standard graph where it would be up 4 and down 4. Our sinusoidal axis is at the x-axis. Actually, we're going to call this theta. That's the theta axis, and this is the r-axis. So it's just a normal period, 2 pi. So we half 2 pi and get pi, and we half again and we get pi over 2 and 3 pi over 2. Just our normal, regular, standard period. Sine starts at the sinusoidal axis, so it's going to start here. Then it goes up, then down, goes like this. Okay, and this is where I'm going to pull my points off of. I'm going to pull it off of this graph. Now, hopefully this brings back memories of us graphing before. Hopefully, pleasant memories, right? I'm sure. So what we're going to focus on are each of these points. So we're going to do this point first, then we're going to graph this point, then we're going to graph this one. We're going to graph the points. So let's start. So we've got 0. So this is, 0. And we need to graph the R measure is 0. So we start right here at the origin or the pole. Then at pi over 2, my point is at 4. So 1, 2, 3, 4. Pi over 2, it's at 4. And one of the most important things that we can, and that's hard to see. Let me change the color. So we're here, 1, 2, 3, 4 here. One thing for us to note is that when we connect these points, it needs to be with a curve. We never ever connect them with a line. And it needs to be kind of plump, if you will. I don't really have a better word to describe it. It's kind of full. So when I make this curve, I'm going to make it nice and full. I'm not going to just, I'm going to try to make it as full as possible. And I'm not really great. Y'all know I'm not a great artist here. So we'll just make it as plump as we can. The plumper, the better. So, okay, so we've got that so far. So what have I done? I've graphed this one, I've graphed, and I've graphed that one, those 2 points. Now let's work on pi 0. We're going to graph this last point right here, pi 0, which actually puts me right back where I started, and I'm able to complete this. Now, this portion of the graph right here, this portion is actually a duplicate. This is a duplicate of what we've already done. And the only reason is because see how we've completed the circle. There's nothing else to do. I could go back around. What that does is it traces it back around. And I could do that if I wanted to. At 3 pi over 2, we're at -4. So that would put me over here, right? And so I would go from 0 to 3 pi over 4, and I'm not drawing it as plump, but it would basically just go right around. I mean, it's the same circle. I didn't draw it as well, but it's the same circle. So it's just a duplicate. And why is that? Well, if we look at this graph right here, what this is, the number times sine or the number times cosine is going to create a circle. And when we create circles, we only need like half of the normal period to create the circle, which I know is unusual, but I mean, that's just the way that it works. It's okay. Okay, so I want to pause here for a second. Are we okay with graphing a circle? Yes.
So how many points did you say it needs to do the whole circle?
For this, just 3. Just the first 3 points, because you start at 0, 0. You go to, pi over, basically 4 pi over 2, and then you go back to 0 pi. So you basically get back, when you get back to where you started, you've completed whatever graph you're graphing when you get back to your start. Okay. Are we okay with the circles? Okay, so this is what a circle with a sine would look like. The circle with the cosine we have right up here is still a circle, but see how it's oriented differently. It's along the x-axis instead of like the circle with the sine here, it's along the y-axis. That's just a pattern that you may want to note if you would like. Okay. So let's take a look at number 2. This one is like the numbers. We've got a number plus a number times sine or cosine. So that's that middle section we were looking at. So this is how much I'm shifted up or down, the 3. And this 3 is actually my amplitude. So when I graph my Cartesian graph, I'm going to shift my sinusoidal axis up 3, because that's what that 3 tells me to do. And then my amplitude is 3, so I would go up 3 and down 3. My period at still b is 1. So that's still going to be a normal, period of 2 pi. So 2 pi, and then half of that is pi. Half of that is pi over 2. So I've got pi over 2 pi, 3 pi over 2, and then 2 pi. Those are just my normal quadrantals on our polar grid. Okay, so that's the setup for us. We've shifted up 3, and our amplitude will be from the sinusoidal axis, up 3 from the sinusoidal axis, and down 3. So sine starts in the middles. So we're going to start right here in the middles. Then it goes up to its max, back down to the middles. Then it goes down to its minimum, and then back to the middles. And so this graph looks like this. Okay, so I'm going to graph each of those points. We're going to graph this point. This is 0, 3. We're going to graph this one. We're going to need to graph all of these points, which you'll see as we're, going through. We need to graph all of them to get back to the start. So I graph at 0, 3. So 1, 2, 3 puts me right here. Then pi over 2, 6. 1, 2, 3, 4, 5, 6. So now we're going to connect those points with a nice plump curve. Always curves, nice and full. Okay, that, y'all know I'm not the best artist. We're just, okay, that's close. That's close enough for me. Okay, so pi over 2, 6. Now we're at pi 3. So we're at pi right here, 3, 1, 2, 3. Again, we're going, when we're connecting these, we're making it nice and full. Okay, well, each one I draw is worse than the other one. So I don't know, ladies, but I guess my left side is not that good. Okay, that's close as I'm gonna get. All right, so we're at pi 3 or 3 pi. Now at 3 pi over 2, which is, you know, down here, we're at 0. So this is where there's danger. I have had students connect this with a straight line. Please don't do that. They're all curved. Now this curve is like a little small curve inside this quadrant right there. That went from, I navigated from pi to 3 pi over 2, so I'm inside that third quadrant, and I just headed towards the r of 0. Now with the other one at 2 pi, we're back out at 3, so again we're going to kind of make it nice and kind of plump as we can, and that's a cardioid. Okay, how is that? Are we all okay? Okay. So this one, number 3, is probably one of the harder ones to graph. I'm just going to be honest with you before we get through it. And that's because, let me show you which one we're graphing. Well, first of all, I want to pause here for a second. So everybody got number 2 down? Everybody have what they need to for number 2? Tell her. This is so fun. Seriously. Okay. So let me show you why this one is a little rough. Well, I'll suspend that. So let's just go and look at what it's going to look like. It's one of these. It's the one with the inside loop. The reason that this is kind of hard to draw for students and for anybody is that this loop right here is like at the origin. So this, where these, see how where they intersect, where those curves intersect right here is at the origin. And that's probably the most common error that I see, is students not putting that intersection at the origin. Okay, I'm just letting you know. So let's see, how do we know that this is one of those? Well, the A and the B are what tell us. I want you to look at the A and the B. Let's compare these two A's and B's. So notice how this A and this B are the same numbers. They're equal. Okay, so let's just make note. I just want you to notice patterns. Notice how this A is smaller. When this is smaller, when that number is smaller, you're going to get the inside loop. So when that number is smaller than than 4, or the B, you will get, so just it will be inside loop. And I'll show you how you can tell on the graph, on the Cartesian graph itself. So that's just a heads up on what we're getting ready to travel into. It's going to be fine. So the sinusoidal axis is shifted up 2. So 1, 2. And the amplitude is 4, so that means I go up 4, 1, 2, 3, 4, and down 4, 1, 2, 3, 4, for our curve. It still has a B of 1. So we have a normal period, so we go out to 2 pi. Half of that is pi. Half of that's pi over 2. So regular old, you know, pi over 2 pi, 3 pi over 2, 2 pi, regular. It's cosine. So cosine starts up at the maximum, which is up here. Then it goes to the middles. Then it goes down below. Then it goes back to the middles. and then it goes to the top. Okay. So on this particular graph, this Cartesian graph, this part right here that drops underneath the x-axis, but for us this is actually our theta axis, that's an indication that I have an inside loop with a problem like this. I know that this number 2 is smaller. The 2 is smaller than this, that was b, little b, and I see that it drops below. So this right here, these 2 points right here are when r is 0. So I'm going to be traveling through the origin at those 2 locations. That's where I'm going to be traveling. So we're going to go kind of slow on this one. So at angle measure 0, we're at 1, 2, 3, 4, 5, we're at 6. So 1, 2, 3, 4, 5, 6. We're right here. Angle measure 0, we are at 6. At angle measure pi over 2, we are at 2. Okay, so let's draw our nice and, plump. Okay. Now, at angle measure pi, we are at -2. At angle measure pi, we're at -2. So we're in here, which causes students to go crazy. They're like, what? And this is where it gets weird, okay? It's weird. So what we have to do, so stay with me, my ladies. What we have to do is, so this portion, let's do this portion of the graph is this portion of the graph. So those yellow highlighted pieces correspond to each other. And then this where I have that pink circled right here, that's when I hit the origin. Okay, so I actually have to go through the second quadrant. Those yellow highlighted pieces are in the second quadrant. Now, when it turns negative, it's very weird. I want us to think about this for just a minute. It's not like, I know there's going to be a circle inside there, but I want you to understand what's going on. So right between here, this is supposed to be quadrant 2. Okay? Between pi over 2 and pi, that's quadrant 2. But it's -r. So instead of being in quadrant 2, where is my graph actually going to be? Since r is negative.
4.
In 4. It's going to shoot me across to 4. So that's why I've got this curve right here. And again, I'm just really trying to be very specific. This curve matches this right here. That's where it came from. Now, you can just know that that's going to be an inside curve. You don't have to follow it like I am. I just want you to see where it comes from. Now, over here, this between pi and 3 pi over 2 is quadrant 3. That's where it is. But am I going to be drawing the curve in quadrant 3? No, I'm going to be drawing it in quadrant 1. Right? I'm going to shoot across to the other side, right? That's what we do when it's negative. So this portion of the graph right here is, and I'll highlight that. This is this pink part is this pink part. Okay. Now we're back into regular regular stuff. So we'll go with blue. So right here, this piece right here, I'm still in quadrant 3. So this is where I go to 2 in quadrant 3, right here. So that's this piece right here. It's all color-coded for you. Yay. Y'all are like, please stop with the color coding. It's okay. You don't need to remember any of that. I just want you to know where everything comes from. And then when we're back at 2 pi, we are back at, what was that, 6? So it takes us back along. So what are we doing? We are making sure that we go through the origin. So the outside, if you will, the outside of this figure looks like a cardioid, doesn't it? If you just focus on the outside, and I'm just going to trace that outside. If the outside, not a good color, what do we, well, green, I guess. If I focus on the outside, that looks like a cardioid, right? It's a cardioid with an inside circle. Okay? All right. How are we on that one? Everybody okay? Okay. Let's look at our next page. We have 3 more to do. These are, like I said, number 3 I think is the hardest. These are a bit easier to me. Okay, so here we go. We've got a double angle. So what do we got? So this is the length of the petal. And this tells me that's an n equals 2. And that tells me that I have 4 petals. That's what the graph, the actual equation tells me. I know that the period equals 2 pi over b. And here b is 2. That's b. And b is 2. So the period is actually pi. All right, so here we go. So the amplitude is 5, so up 5 and down 5. The period is pi. So half of pi is pi over 2. Half of pi over 2 is pi over 4. So 1 pi over 4, 2 pi over 4, 3 pi over 4, pi. It's cosine. And cosine starts at its max. Then it goes to its middle. Then it goes to its minimum. Back to the middle. Back to the max. Hopefully this, the more we work on it, the more you're reminded of us working on this several weeks ago. Now, when we're working on the roses, this is 1 full petal. Okay? That is 1 petal. We don't have to graph the complete Cartesian graph to be able to understand where these are. If we can just start the petals, we can just use symmetry and finish them all out. We know we're supposed to have 4 petals. So what I would like to do, let's just start at, so remember this is theta and this is r. Start at 0, 5, 1, 2, 3, 4, 5, okay. And then at pi over 4, we go to 0. So I see there's a half a petal right there. And I certainly know how I can finish the petal out. Now I'm going to skip to the next petal, the full petal, just so we can make sure we're in the right spot. So at pi over 2, we're at -5. So that shoots us across the other side, 1, 2, 3, 4, 5, right here. And I know that's the tip. Those are the tips of the petals. So I know that's going to come out like this. And that petal is actually the exact same one. This is the yellow one. This is the one that is appearing on our Cartesian coordinate. Those are identical. Now, with that much of it drawn, I think we can figure out how to fill in the rest, right? We don't need to keep graphing the Cartesian graph. We can just fill in all the other spots. Do y'all see how that's going to come about? Does that make sense, how we'd fill that in? So let's just fill that in. So I'm going to complete this petal. I know I have one above, 1, 2, 3, 4, 5. I know I have one up here, so I'm just going to draw that petal in. I know I have one over here, 1, 2, 3, 4, 5, and I have my whole graph. Okay, how we doing? Good. So symmetry, we're going to use symmetry. Once we figure out where the petal is, just draw the petals. Don't worry about continuing the Cartesian coordinate graph. Okay, so let's take a look at number 2. All right, so this is the length, 6 is the length of the petal, and this is an N of 3. That means we're going to have 3 petals. That's what that means. When it's odd, it's the same number. Okay, all right, well, B is 3, so period equals 2 pi over B, and B is 3. So this period is 2 pi over 3. Okay, here we go. So the amplitude is 6, so up 6 and down 6. My period is 2 pi over 3. Half of 2 pi over 3 is pi over 3. Half of pi over 3 is pi over 6. So 1 pi over 6, 2 pi over 6, 3 pi over 6 reduces to pi over 2. And those are my angle measures. Again, that's theta and that's r. Okay, it's sine. So sine starts in its middles, then goes up, then back to the middles, then to its lowest part, the minimum, and then back to the middles. And what we actually have here, we actually have 2 petals that are completely drawn here. 2 complete petals. So I'm going to draw the first one. So I'm just going to, this pink one. So let's work on this pink petal. All right, so let's see. We start at 0, 0. Then at pi over 6, we're at 6. So 1, 2, 3, 4, 5, 6. So right here, that's the length of the petal. So we just draw it out. And I'm just going to color code it. So this is the pink one. Okay, so those correspond to each other. Okay, the next one, let's see, I'm going to color this one blue. So this one is blue. I go to pi over 2, and pi over 2, it's a negative 6. So it shoots me across to the other side. 1, 2, 3, 4, 5, 6. It puts me down here, so that's the tip of the petal. And let's just completely draw the petal in. And this would correspond to the blue one. Now, if you wanted to complete the Cartesian graph, you could, but we really don't need to. This is perfectly symmetrical. It's perfectly symmetrical. So which quadrant do you think our third petal is in?
2.
Yeah, it is. It's in the second quadrant, isn't it? It's because that's where, to be symmetrical, that's where it would need to be. And what angle measure is the petal going to reach out to? The tip of the petal is going to be at what angle? 5 pi over 6. That's where it's going to be. So let's go ahead and just graph it in. 1, 2, 3, 4, 5, 6. So we're at 5 pi over 6. We're going to fill out that petal. Okay.
How did you know it was at 5 pi over 6?
Be
One is quadrant, one is pi over 6.
Yeah, and it has to be perfectly symmetrical. It has to be symmetrical. So if we folded it on the y-axis, those petals would have to meet up. It has to have a symmetry. Okay, how are we doing with the odd ones? Everybody okay? Okay, one more. And this is the little r squared little one. Okay, this is our r squared friend. So what we want to think about we want to think about square rooting both sides. I mean, I'm not going to physically like work that out, but what I'm going to graph is 4 sine 2 theta. That's what I'm going to graph. I recognize that instead of 4 petals, I'm only going to have 2 because the r squared eliminates the negative petals, and I'll show you what that means as I graph this Cartesian graph. So we graph the Cartesian graph. I'm graphing 4 sine 2 theta. That's what I'm graphing. And why is it a 4? Because the square root of 16 is 4, right? That's why it's 4. So up 4 and down 4. It's a double angle, so we figured out on the other side that that's period is pi. So that means that's pi over 2, pi over 4, 3 pi over 4. Okay. It's sine, so sine starts in the middles, then goes up, then goes back to the middles, then goes down. And this is what we look like. Okay, so we're going to graph this petal right here. I'm going to color code it in yellow. This is the petal we're going to graph. So I start at 0, 0. I go to pi over 4, and I go 4 rings out. So 1, 2, 3, 4. And that's the tip of the petal, so I'm just going to complete it. Okay, so this is the yellow one. Now, the petals that fall underneath the x-axis are not, we cannot graph those. That's not okay. So normally we would have a petal, you know, over here. That's where we put the petal over here. Because it's negative, it would shoot us across. We don't have a petal there because it's imaginary. Okay, I guess there's an imaginary petal over there. We can think about the poor little imaginary petal. And we could finish the Cartesian graph if we wanted to, but I also know this is symmetrical. It's perfectly symmetrical. So which quadrant does the other and final petal have to be in? Quadrant 3. It has to be in quadrant 3 because this is perfectly symmetrical and there's only 2 of them. And so let's go at, and it'll be at 5 pi over 4 because that's directly across from pi over 4. So let's go out 4. 1, 2, 3, 4. And there's our final petal. Okay? So the r squareds are always, the petals are always directly opposite each other. They're not beside each other.
Just so for r squared, would there only be 2 petals?
Yes, ma'am. Only 2. The other 2 are imaginary petals. I feel sorry for them that they can't be there.
Cross it out because r squared can't be negative.
Right. Because r squared, so if we looked at this equation and we know that r squared has to be 16 sine 2 theta, this is always a positive number. R squared is always a positive number, which means this is always has to be a positive number. We're not allowed to have negative numbers in this scenario. That basically makes it imaginary. It's like the square root of a negative number would be imaginary. Okay?